Good morning, everybody. Welcome to your study part. We'll be looking at physics today with reference and emphasis to your Jamb examination. Here are the highlights of what we'll be doing in the course of the class. As you well know, physics is actually divided into the following branches. We have mechanics, heat and temperature, and wave, waves with specifics to optics and sound, electricity, as well as magnetism, then atomic physics. Atomic stroke nuclear physics. In the broad view of things, for you to actually ace your examination with specific physics, you have to familiarize yourself with the concepts surrounding these branches of physics. And that's why we're here in class. So I'll be leading you and guiding you through each of these branches as to how questions are asked in your Jamb examination. So we try as much as possible to pick topics involving these areas along the line. I give you the explanations, the key areas to focus on, as well as patterns to which questions are asked for each topic. Let's get right into it. Now, first up, we have electricity. There are certain technicalities to electricity subject to the topics you have under it. You are going to find under electricity, capacitor. You are going to have questions with regards to cells. You're going to have questions with regards to resistor. You're going to have questions. Now, this is with emphasis on current electricity. Don't forget, we have current electricity and we have AC circuits. AC circuits actually focuses on a bigger dimension. So, in the concept of what I'm writing first, I'm actually making emphasis on current electricity, under which you have your Ohm's law, V equals to IR. We have capacitor, we have cells, we have resistor, we have questions with regards to power and energy, generation or consumption, among other things. So, resistivity will also find its way here. So let's start this. Resistance and resistivity. So, these are what we'll be looking at covering under electricity. Remember, power consumption also falls under this instance. When you know how to calculate the wattage which you consumed, then it's easy for you to convert it into what? The cost value for such questions. Now, let's get started. Picking first, capacitor. What does Jamb expect you to know under capacitor? Here are the key highlights. Certainly, capacitors are actually devices that get to store charges and electric energy in very small amounts. We have that the unit of capacitor is farad. Capacitor is measured in farad. You have that once you are seeing alphabet F in any question, because you must know that what the unit to any physical quantity in physics is the sellout as to what formula you want to use. You can't start wrapping your heads around so many formulas when you can't actually place the right unit where it should belong. We have that capacitors are actually devices which actually store electric energy in farads. So once you see capital F in your question, then you know that they're making reference to what? Capacitor. Here is the keynote. Sometimes you might be given the value of capacitance in a question in microfarad. Microfarad. So you would never see them write micro in full this way. You're expected to know that what you'll be saying will be micro, mu f is what you see in questions. Mu f. You get to understand that questions majorly are actually calculated in microfarad most of the time. And this is the sellout. Your microfarad is a representation of times 10 raised to power minus 6 farad. Meaning that when you are giving questions, always know that mu f is serving a purpose of holding the value of 10 raised to power minus 6. Put that in mind. Then we can now come to the basics of capacitors connected in series as well as capacitors connected in parallel. I'm sure most of you are already familiar with the concept of resistors in series and resistors in parallel. We have that capacitors actually share the opposite formulas which resistors actually possess. This is what I mean. Capacitors in series. Capacitors in series. You are going to have the diagram this way. Here, the length of the two terminals are actually equal and the same. The length of the two terminals are always equal, and that makes this capacitor symbol different from your cell. Cell is denoted this way, positive and negative terminal. But in the case of capacitor, we have them of equal length. So don't mix it up. When questions are given to you with respect to capacitors, check out the length of the two terminals drawn for you. Are they of equal value or of equal length or of varying length? So on this note here, we can easily say that the first capacitor represented by C1 and this guy represented by C2. We can calculate what the capacitor in series is. And how do we get the value? We simply say that capacitor in series can be calculated not as a direct addition value which we have in resistance. What we are having now will be the inverse value which will have happened under resistance in parallel. This is what I mean. 1 over C series becomes equal to 1 over C1 plus 1 over C2. See what happens. Here under series, you are having a flip over. You are taking the inverse addition here. Unlike your resistance, whereby you take direct addition. Now, here is it. We have the formula this way. For capacitor in parallel, capacitors in parallel, rather than have the inverse addition, which you are going to have under resistance, you are now going to have a direct addition, which is spelled out this way. C parallel with the diagram first. C parallel now would have the formula that says C parallel becomes equal to C1 plus C2. Note what happens here. What we'll have done under series connection is what we are doing under series connection for resistance is what we are doing for parallel under capacitor. So what you know under resistor, just know that it's an alternate to what we have under capacitor. But note, Jamb is not very silly. They know that most of you end up cramming formulas. That is what your major expertise is, cramming formulas. You are going to be sold out and surprised by the pattern to which Jamb is going to present questions. Why? Once you don't get a clear understanding as to how to identify connections in series and connections in parallel, then you won't be able to solve questions under capacitors. Here is the secret to knowing it. Now, we have identified connection in series. We have identified connection in parallel. How does Jamb pose questions to you? Imagine a diagram this way. And please note, capacitors do not what? Support the flow of current. Capacitors do not allow what? Current flow through them. What we have flowing through capacitors is what? Charge. Note that. Charges flow through capacitors. Current flow through resistors. That's why we have V equals to IR. V equals to IR under what? Resistors. For capacitors, we have charges flowing through. As such, we have a formula to that effect. We'll get right into that later. Now, if you have this diagram, how do you identify a series connection and a parallel connection? Very key. Watch. If charge value Q is flowing this way, you must expect that tracing your circuit diagram, the moment charge or current is flowing through any circuit and the flow of circuit is such that it is unidirectional, meaning it can flow through only one direction, then that connection pathway is actually a series connection. But whenever there's a flow such that the flow will get to a terminal point whereby it can split into two or more sections, then you are having a parallel connection. This is what I mean. Imagine this charge flowing here. Entering into this capacitor, we have a series connection for the fact that what? It just flows through, comes out. No problems. But when the charge gets to this point, what happens is this. It can either choose to move up, it will what? Split into two. Some section of the charge will flow up into the first capacitor up. Let's assume C1, C2, and C3. You are going to have that what? Some amount of the capacitor is actually going to flow upwards, some will flow downwards. The moment you're having charge to split up into two or more sections, then that circuit part is actually a parallel connection. So, it means that C2 and C3 are actually connected parallel to each other. C2 and C3 are actually parallel to each other. Now, the secret is this. When you are given questions whereby you have two or more capacitors, two or more parallel connections in a given place, you merge them together into one. You use this formula here for parallel to find the combined capacitance. You have to calculate the combined capacitance this way. Now, here we go. If a diagram is given to you this way, remember when it flows here now, when some of the charges flow through this part up to this point, the ones flowing to this part gets to this point. They tend to combine together and continue flowing as a whole to enter this what? Capacitance 4 in series. So these two are in parallel to each other. This is series. So it means you are going to merge these two together, C2 and C3. Merge them together such that it becomes one, and we are now going to have all series connection. That being settled out, we are going to look at questions, not to worry. Take a look at the next diagram. If you are given a diagram this way, we have this, we have this, we have this, and we have this. Mind you, watch the length of the connection given. C1, C2, C3, C4. How would you describe the connection here? Is this a series connection or a parallel connection? Your guess is as good as mine. Some of you would call it what? A parallel connection, and that would be absolutely wrong. Why? This is a given loop. There's no specifics as to the start of what? The connection. But let's pick any parts along the circuit diagram. Let's pick this place here now. If the charge is to flow along this path and it enters the first capacitor, C1, what happens is it is going to come out. Series, since there's no obstruction, it comes out and it gets to this point. At this edge here, it is expected that what? It has only one turning point next. It is to turn downwards. Since we have only one direction to turn to in the flow of charge, then it means the relationship between this part and this part is what? A series connection, not a parallel. Why? only a single what? Flow through. It is to turn downwards. As such, this guy, C1 and C2 are in series with each other. Watch what happens. When the charge flows through C2 and gets to this point, at this point here, it also allows what? A single direction. It can only flow through what? A single pathway, which is to turn what? To the left. So it flows to the left, a single path. As such, this guy is actually in series with C2. Lastly, C3 and C4. C3 and C4. Observing this, we have that what? C3, at this point here, the charge will easily flow upwards into C4 and the loop continues. So we have that all these capacitors are actually connected in series and not in parallel. Now you have identified how to what? Figure out which pathway identifies series connection or a parallel connection. Watch this. When we are given this, C1, C2, C3, C4, C5. Let's have this. Now, given a circuit this way, let's figure out which and which are in series, which and which are in what? Parallel. We'll spell out that when the charge is flowing, it first flows through what? C1. Flowing through C1 as a what? Series connection. It's expected that it gets to this point and splits up. The moment you're having a splitting up, that means that what? A parallel connection exists. But here's the catch. When some of the charges tend to move upwards, it passes through C2 and C3. The relationship between C2 and C3 is that they are in series to each other. Why? There's only one direction that links your C2 and your C3 together. So these two guys are in series. C2 and C3 are in series. C4 and C5 as well are in series to each other. C4 and C5 are also in series. As such, we can now say that what? The combination of what? C2 and 3, meaning that what? Having joined 2 and 3 together, is in parallel to C4 and C5. When you calculate the series connection of C4 and C5, you are having that what? They are going to be in parallel to C2 and C3 up here. Then we have a close-up here, and the charge continues flowing. All being said, let's get to look at how questions are posed to you, talking about your Jamb examination. But before then, have it at the back of your mind that we have a way of linking capacitor to other parameters in physics, talking about your charge and your voltage value. So, in the case of voltage value, all you have to put in mind is that what? Q is equal to CV remains the key formula you use. Charge, energy stored in a capacitor. Talking about energy stored in a capacitor, first you must understand that the relationship between the charge flowing through a capacitor with respect to the voltage is CV. Q equals CV. Have that at the back of your mind, and you easily figure out that what? Energy in this sense is half QV. This represents all the formulas you need under capacitors. This represents the larger majority. I wouldn't say all. It represents the larger majority because there can be a twist to it asking you to what? Calculate the capacitance of a parallel plate capacitor. So if that comes into place, then this would not fit in. This would be what you'll be using. Capacitance will be equal to, check it out, epsilon naught A over D. Capacitance is equal to permissivity of free space multiplied by the cross-sectional area of space divided by E. distance apart between the plates. So this will only come in when you are given a parallel plate capacitor and we're asked to calculate the capacitance. So all these formulas here, let's look at questions in the light of these questions. So now you're familiar with the aspects we'll be touching under your physics before your examination. Mechanics, heat and temperature, waves involving light and sound wave, electricity, magnetism, as well as atomic and nuclear physics. Question 1. We are told to calculate the effective capacitance. That's how your Jamb exam poses the question. Calculate the effective capacitance in the diagram below. Here's the diagram. We have that this guy is linked to this guy. As such, this part is linked to this. And we have 2 microfarad here, 2 microfarad, 2 microfarad, 2 microfarad. Calculate the effective capacitance for circuit indicator. So here is it. As discussed earlier with regard to the flow here, we say that whenever the charge is flowing, it gets to this point and splits, meaning that capacitors at that region, at both regions, are actually parallel to each other. So it means that what? This and this capacitor and this capacitor are actually parallel to each other. Since we have others in series, this guy is in series. When it splits, they join together here and continue. We calculate the combined capacitance for these two values first. As such, we have that C parallel becomes equal to C1 plus C2, representing the first two. So we are going to say that C parallel becomes equal to 2 plus 2, and that becomes 4 microfarad. The new diagram becomes something like this. So what you observe here is that what? This 2 microfarad, here is it. This 2 microfarad, here is it. But these two, the upper and the lower value microfarad, have been merged together using parallel connection formula. Using parallel connection formula, that is what? Direct additive to get your 4 farad. And this is what we have. Normally, these two merged together becomes 1, and it is in series with others. So, using series formula, we need to say that 1 over C series should be equal to 1 over C1 plus 1 over C2 plus 1 over C. 1 over C series will be equal to 1 over 2 plus 1 over 4 plus 1 over 2. C series equals LCM being 4. We have 2 plus 1 plus 2 here. 1 over C series become equal to 5 over 4. Cross multiply. We have the 5C series. 5 times C series is equal to 4. Divide through by 5. We have that C series becomes equal to 0.8 microfarad. So the total effective capacitance in this case is actually 0.8 microfarad. It's actually 0.8 microfarad. Pushing forward, we have the next question here that links up capacitor with respect to what? Charge and voltage. And please note, what applies to currents under resistors applies to charge over here. And exactly what happens to voltage under what? Resistor is what happens to voltage here. What do I mean? Voltage in parallel are actually equal. voltage in series are actually what? Additive. Charges, we said that current flowing in series